Let's talk about the moon, our closest celestial neighbor. It hangs in our sky, a familiar silvery disk. But there's a part of it we never see from Earth. We call it the far side. Now, many people also call it the dark side of the moon. This is a common misconception. It makes you think of a place shrouded in permanent darkness, but that's not quite right. The far side of the moon gets just as much sunlight as the near side. It goes through its own day and night cycle, just like the side we see. Each lunar day lasts about 2 Earth weeks, followed by 2 Earth weeks of night. So it's not perpetually dark at all. The term dark side probably comes more from the mystery surrounding it. For most of human history, we had no idea what it looked like. It was hidden from our view, a blank canvas for our imaginations. What secrets could it hold? What strange landscapes might exist there? This sense of the unknown, this darkness in our knowledge, is likely why the name stuck. But scientifically speaking, far side is a much more accurate description. It simply refers to the hemisphere of the moon that is always turned away from Earth. It is a place of intrigue, not because of a lack of light, but because of its hidden nature for so long. Think about it. Every night you look up and see the moon. You see its craters, its seas, the Maria as we call them. These are familiar features. But imagine there's a whole other half you've never laid eyes on. It's like knowing someone your whole life but only ever seeing one side of their face. The far side remained a complete enigma until relatively recently in our technological history. This hidden face naturally sparked curiosity and, yes, a lot of speculation. What wonders, or perhaps even what beings, could reside on this unseen portion of our lunar companion? So when we discuss the far side, remember it's a sunlit landscape, at least part of the time. It has its dawns and its dusks, its scorching days and its frigid nights. The real mystery wasn't about a lack of photons, but a lack of observation. It was a frontier waiting to be explored, a page in our cosmic neighborhood story that was, for millennia, left unturned. Understanding this distinction is the first step in appreciating the true nature of the moon's other half, and the ongoing quest to uncover its secrets, including the tantalizing question of whether it could harbor life. So why is it that we never see this far side of the moon from Earth? The answer lies in a fascinating cosmic dance called tidal locking. It's a phenomenon that's not unique to our moon. Many moons in our solar system are tidally locked with their parent planets. Essentially, the moon rotates on its own axis in exactly the same amount of time it takes to orbit the Earth. This perfect synchronization means that one side, the near side, constantly faces us. The other side, the far side, is perpetually turned away from our direct line of sight. It's a gravitational embrace that has lasted for billions of years. This tidal locking didn't happen overnight. When the moon first formed, it likely rotated much faster. But over eons, Earth's gravity exerted a tidal force on the moon. Think of it like the moon creating tides on Earth, but in reverse and much stronger on the smaller body. This gravitational tug-of-war caused the moon's rotation to gradually slow down. Eventually, its rotation period matched its orbital period, and it became locked in this synchronous rotation. It's a stable configuration, a consequence of fundamental physics playing out on a grand celestial scale. So, the far side isn't hiding deliberately. It's just the result of this long, slow gravitational dance. For centuries, this meant that half of the moon was completely unknown territory. Philosophers, astronomers, and storytellers could only speculate about what lay beyond our view. Was it similar to the near side, or was it vastly different, perhaps holding secrets too strange for our comprehension? This lack of direct observation fueled countless myths and legends. It was a genuine mystery, one of the last uncharted territories in our immediate cosmic vicinity. The desire to finally see this hidden hemisphere was a powerful motivator for the dawn of the space age. Humanity has always been driven by the urge to explore the unknown. This cosmic choreography has profound implications. Because one side always faces away from Earth, it's shielded from the radio noise generated by our planet. This makes the far side an incredibly valuable location for radio astronomy, allowing us to listen to the faint whispers of the universe without earthly interference. But before we could even dream of telescopes there, we first had to get a look. The story of how humanity finally unveiled the far side is a testament to our ingenuity and our unyielding curiosity about the cosmos. The hidden face of the moon was a challenge, and we were determined to meet it. The year was 1959. The space race between the United States and the Soviet Union was in full swing. And it was the Soviets who achieved a monumental first in lunar exploration. Their Luna 3 spacecraft flew around the moon and for the very first time in history, captured images of its hidden far side. Imagine the excitement back then. For millennia, humans had gazed at the same lunar face. Suddenly, we were about to see the other half. It was a pivotal moment, a true leap into the unknown, changing our perception of the moon forever. The images transmitted back by Luna 3 were grainy. They were low resolution by today's standards, of course, but their scientific and cultural impact was immense. They revealed a landscape that was strikingly different from the near side. The vast, dark plains of basaltic lava, the Maria, which are so prominent on the near side, were largely absent on the far side. Instead, the images showed a surface that was heavily cratered, almost saturated with impact scars. It was a rugged, ancient-looking terrain telling a different story of its geological history. This was a genuine scientific shock. Scientists were astonished. Why would the two sides of the same moon be so different? The initial photographs, though blurry, sparked a flurry of new questions and theories. The far side wasn't just a mirror image of the near side, it was its own unique world. The lack of large Maria suggested that the crust on the far side might be thicker, preventing magma from easily reaching the surface to flood large basins. This first glimpse provided crucial data, forcing us to rethink our understanding of lunar formation and evolution. It was a classic example of exploration leading to unexpected discoveries. The Luna 3 mission was more than just a technological triumph. It was a profound expansion of our cosmic horizons. It peeled back a veil of mystery that had shrouded the far side for all of human existence. Those first fuzzy pictures represented a new era of lunar science. They demonstrated that even our closest celestial neighbors still held surprising secrets. And naturally, with this new view came new speculations. If the geology was so different, what else might be different about this hidden hemisphere? The quest to understand the far side had truly begun, all thanks to a small, intrepid spacecraft. As we gathered more data from subsequent missions, the stark geological differences between the moon's near side and far side became even clearer. The near side, the one we always see, is characterized by those large, dark, smooth areas called Maria, or seas. These are ancient volcanic plains, formed when massive asteroid impacts created huge basins that later filled with molten lava. About 30% of the near side is covered by these Maria. They give the man in the moon its familiar features. These formations tell a story of a geologically active past, with volcanic eruptions shaping its surface. Now contrast that with the far side. When we finally saw it, thanks to Luna 3 and later missions like NASA's Lunar Reconnaissance Orbiter, we found a very different landscape. The far side is almost entirely devoid of large Maria. Instead, it's a rugged, heavily cratered highland. It looks older, more battered by eons of impacts from asteroids and comets. The few small Maria that do exist are much smaller and shallower than those on the near side. This fundamental dichotomy, this two-faced nature, is one of the moon's most intriguing geological puzzles. Why such a dramatic difference? The prevailing theory points to differences in crustal thickness. It's believed that the lunar crust on the far side is significantly thicker and more ancient than on the near side. This thicker crust would have made it much more difficult for magma from the moon's interior to erupt onto the surface and form extensive Maria, even when large impacts occurred. On the near side, the crust is thinner, allowing magma to well up more easily. This asymmetry might be linked to the way the moon formed, possibly related to the Earth's gravitational pull or the heat distribution in the early moon. This difference in geology has significant implications. The far side surface, being older and less altered by volcanism, preserves a more ancient record of impacts in the early solar system. It's like an older, less retouched photograph of the moon's history. Furthermore, the far side hosts one of the largest and oldest impact basins in the entire solar system, the South Pole Aitken Basin. This colossal crater, nearly 2,500 kilometers in diameter and 13 kilometers deep, is a prime target for scientific investigation, as it might expose material from the moon's mantle. Understanding these two distinct faces is crucial to piecing together the full story of our moon. Section 5, A Hostile Realm, The Challenges for Life on the Moon. Let's be clear, the surface of the moon, whether it's the near side or the far side, is an incredibly harsh environment for life as we know it. It's not a friendly place. First, there's virtually no atmosphere. We're talking about a vacuum more perfect than anything we can easily create in a lab on Earth. This lack of atmosphere means there's no air to breathe, no pressure to regulate, and no protection from the harsh realities of space. It's a stark, silent world where sound cannot travel and where liquids boil away instantly. Then, there are the extreme temperature swings. Because there's no atmosphere to trap heat or distribute it, the lunar surface experiences brutal temperature changes. During the long lunar day, which lasts about 2 Earth weeks, temperatures can soar to over 120 degrees Celsius or 250 degrees Fahrenheit. That's hotter than boiling water. Then, during the equally long lunar night, temperatures plummet to around minus 170 degrees Celsius or minus 274 degrees Fahrenheit. Any organism would need incredible adaptations to survive such violent thermal cycling without a very sophisticated shelter. And if that wasn't enough, there's the radiation. Without a protective atmosphere or a global magnetic field like Earth's, the lunar surface is constantly bombarded by intense solar radiation, solar flares, solar wind, and cosmic rays from deep space. This radiation is damaging to DNA and living cells. Astronauts on the Apollo missions wore specialized suits for protection. But long-term exposure would be a serious health hazard. Any life would need significant shielding, perhaps by living underground, to avoid being fried by this constant barrage of high-energy particles. Finally, the lunar surface is also peppered by micrometeoroids. These are tiny particles of space dust and rock traveling at incredible speeds. While small, they can still cause damage. Over geological timescales, they contribute to the erosion of surface features and the creation of the fine lunar dust, or regolith, that covers the moon. So, while the idea of finding life on the moon is captivating, the surface conditions present formidable, perhaps insurmountable challenges for any known form of life. It's a desolate, beautiful, but ultimately hostile landscape for unprotected biology. Section 9, the next frontier eyes on the lunar far side. So, what does the future hold for the far side of the moon? It remains one of the most compelling destinations in our solar system. One of its unique advantages, as we've touched upon, is its radio quietness. Shielded from the cacophony of radio waves generated by human activity on Earth, the far side is arguably the best place in the inner solar system to build large radio telescopes. These instruments could listen to the faint whispers from the early universe, study distant exoplanets, and perhaps even search for signals from other intelligent civilizations. It's a pristine environment for peering deep into cosmic history. Now let's indulge a little. If extraterrestrials were indeed out there and wanted to keep an eye on humanity's development, the far side would be an ideal, discreet observation post. It offers a stable platform, always facing away from us, yet close enough for detailed surveillance if they possessed advanced technology. While this is pure speculation, it's a thought that highlights the strategic nature of this hidden lunar real estate. However, scientists are more focused on the tangible benefits, like radio astronomy and understanding lunar geology, than on looking for alien lookouts. Interestingly, despite its proximity, the far side of the moon is arguably less explored than the surface of Mars in some respects. We've had numerous rovers and landers on Mars providing extensive ground truth data. The far side, until Chang'e 4, had never been visited by a lander. Our knowledge of it was primarily from orbiters. This is changing though. There's a growing international interest in exploring the far side further. Upcoming missions from various space agencies aim to land in different regions, collect samples, and deploy new scientific instruments. It's a new lunar race, but this time, with more players and broader scientific goals. The far side of the moon truly represents the next frontier in lunar exploration. It holds clues to the formation of our Earth-Moon system, the history of impacts in the solar system, and potentially, resources that could support future human endeavors in space. Whether it's searching for water ice, drilling into the South Pole Aitken Basin to sample the lunar mantle, or building unprecedented astronomical observatories, the far side beckons. It's no longer the dark side of mystery but a bright beacon for scientific discovery and human ingenuity. The quest to understand and utilize this hidden half of our moon is well underway.